Hi everyone, this is the introduction to chapter 4. It is electric potential. In this chapter, we are going to be talking about electric energy. And the first concept we need to talk about is the concept of a conservative force. We've seen in mechanics that a conservative force, the energy or the work done against the conservative force only depend on the starting and ending point. Gravity is such a force. It happened that the electric force is also a conservative force. So therefore, we can define mathematical value for the potential energy when it comes to the electric force. So before we do that, we need to recall what is the fundamental concept of work. And work is defined as the dot product between the force vector multiplied by the displacement vector. Now it's possible that your teacher in mechanics did not taught it that way. He maybe have just mentioned that the work done is equal to the force multiplied by the displacement multiplied by the cosine of the angle between these two. Both methods are completely equivalent. All right. Now, when we were dealing with the gravitational force, from the point of view of the surface of the Earth, if you stay close to the surface, the force is relatively constant. Therefore, you have a constant gravitational acceleration. When it comes to the electric force, some small change in the distance from the charge can create a big change in the electric force. Therefore, we cannot assume the force to be constant throughout the displacement. All right. So that means we need to integrate the force over the complete displacement. So this is how we are going to do it. And by the way, it's possible at this point that you did not do much calculus. Don't worry, I will not ask you to do any calculus in the first test, maybe in the final, but in the first test, I just want you to be able to apply the conclusion from this derivation. All right. So the work done will be equal to the integral of the force multiplied by the derivative of this displacement, ds, multiplied by cosine of the angle. Now we assume that the angle here stay constant throughout the entire motion. All right. Now, because it's a conservative force, the only kind of displacement we care about that will affect the work done is the displacement against the radius of the charge. In other words, we care, are you approaching or moving away from the charge? That's all we care about. So we are going to replace the ds by a dr over here. So the derivative of the radius, so the change from the distance from the center of the charge to where you're bringing your second charge. All right. Now, in order to simplify all of this, we are going to do one derivation. And that derivation involves the work done to move a charge from infinity to a distance r. All right. So in order to do this, we use the integral, but we have to set a lower and upper bound. So we bring a charge from infinity to a distance r. Now you can imagine that you have a charge set in place and it's a positive charge. You bring another positive charge from infinity to a certain distance r. While you are bringing that charge from infinity, if both of them are positive, that means the force will be pushing in that direction. The displacement will push in the opposite direction, which means that your angle between the displacement and the force will be 180 degrees. So now we have a lower bound, it's infinity. Our upper bound is the radius r. We know our angle. We replace the force by the Coulomb force, which is Coulomb constant, multiplied by the first charge, multiplied by the second charge, divided by r squared. Now, the Coulomb constant and the two charge are constant. We can extract it from the integral, and we will end up with an integral of 1 divided by r. We need to evaluate it on both bound. Again, if you did not do it in math yet, don't worry. The result is the work done will be equal to the Coulomb constant multiplied by the two charge divided by r. Notice it went from r squared to r, and this is a potential energy. Now, when we deal with potential energy, we're not talking about vector anymore. So the sign of the charge here will indicate if the potential energy is positive or is negative. Now, just to get a physical sense, if you have a positive charge, and you bring it from infinity, since they repel each other, you're creating energy. They fight to repel each other, which means you could release the charge and it will swing back in the other direction. In other words, you are increasing the potential energy. If you add two different charge, they will try to attract each other. So you build potential energy by moving them farther away from each other, all right? If you release them, they will come back, all right? So if the two charges are the same, this term will be positive, which means as you are taking a charge from infinity and bringing it closer, you are increasing the potential energy. If one of these charges is positive, the other is negative, then the potential energy will be positive if you're moving the charge further away, and it will decrease once you release them and they come back together, all right? So one last formula is, instead of, one way we could calculate the difference in energy, let's say you have a charge again, two positive charge, they are at a meter apart, and you want to move one of the charge such that the distance is now 0.5 meter apart. You could redo this integral, right? It starts at 1 meter, goes to 0.5 meter. That will work. But I want to avoid having to use integral and calculus at this point. So what you could do is calculate the energy to bring a positive charge against another positive charge from infinity to 0.5 meter, minus the energy it took to take that same charge from infinity to 1 meter. It's a way easier method to arrive exactly at the same value, all right? Now, this formula is way easier to comprehend while solving some example. That's what we're going to do after the next video, all right? So that's it for the first introduction to electric potential. We are going to talk about the voltage in the next video. All right, so see you in the next video.